What is up, guys? This is my first attempt at doing one of these PowerPoint video things. I think it's pretty cool. Seems like I can do quite a bit of interesting stuff on here. So yeah, let's give this a try and see how well it goes. This is Mr. Coulomb. He is the one who came up with Coulomb's law for the electric field, which we started talking a little bit about yesterday. So let's see how it goes today. So we've been studying electrostatics. Electrostatics is the study of the forces that are on charges when they are at rest. So remember when we were talking about kinematics, there's statics and dynamics. So statics specifically is the study of stuff that is not changing. So here this means that we have electric charges that are at rest. They're not moving, they're staying in one place. So it's just a nice snapshot of that one singular moment, and we don't have to worry about things moving around. We can worry about that later, but for now, this is just when stuff stays where it is, stays the same. Uh, when things start to move, that's when we start getting into things like electric current, which we will deal with in the next chapter. But for now, don't worry about that. If you remember, we talked a little bit about how negative and positive charges are what we see for electric charge. When we have like charges, meaning charges that are the same, kind of like we've got here, we have this charge here and this charge here, they're both negative, and so they repel. But then when we have charges that are different, like this positive and this negative, they attract. So like charges repel and opposite charges attract. You've probably heard opposites attract. Well, this is an example in science where that is very much the case, that our positive and negative charges attract one another. They feel a force that pulls them together. So here we have Charles Coulomb, same guy from the very beginning. We're missing his little mustache though. There we go. So he was born in 1736, died 1806, as you can see. He sought to measure the force between charged objects. So he saw this phenomenon and wanted to investigate it, learn more about it. So he started taking measurements of different charged objects to see if he could manage to figure out what the value of charge was. Now, he wasn't able to get an exact value, but he could find the ratio between different charged objects, which isn't exactly the same, but we learned quite a lot from his experiments. So the way he did it is pretty incredible. He actually prepared a torsion balance, which you'll see a picture of it in a moment, and he had these different charged spheres and measured the torque that was generated by those forces. So let's take a look at a picture of what that looks like so you can see exactly how that worked. Okay, so here is a nice illustration of what a torsion balance looks like. So you can see that we've got these gilded pith balls that are right here. Oh, let me get my pen. That are right here. So pith is a material that you find in plants, such as inside the rind of an orange or other citrus fruit. You know, that white spongy material that's right underneath the rind? That is pith. There's also other plants like walnuts or bamboo or other types of trees. It's a really fibrous or really spongy type of material that's found inside plants, and it's actually a really great insulator, so it's able to hold charge really, really well. So that's why it was used in this kind of way to produce this torsion balance. So what Coulomb did is he took these two these two spheres and he charged them and set them up so that this rod right here is balanced from its center, hanging from a wire. Now that wire resists being twisted. You know, if you imagine trying to twist a wire, it wants to twist back. It wants to restore itself back to the way it was. Kind of like if you remember from our from any unit that we've done on springs, there's a certain amount of elastic energy that's stored when you compress or stretch a spring. Well, there's a rotational version of that too. If you start to twist the wire wants to go back to the way it was, so it resists that twist and tries to return itself to its original place. So as you twist this rod, if you wanted to twist this rod around in a circle like this, then that wire is going to say, hey, 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 I want to go back to the way I was. So it's going to try to resist it. And that requires a certain torque or a certain force. Remember, torque is just a rotational force. So by having these two pith balls charged, say we have two positive charges, then that's going to be a repulsive force. So it's going to try to repel the charge just like that, and that's going to provide a torque that's going to cause this it's going to try to cause this rod to actually rotate in a counterclockwise way. Now when it does, you see at the top there's this little arrow here. Well, you can attach a little needle to the top of that wire that turns and touches these different these different parts of a measuring device in order to show exactly how much torque is being generated, which then you can use the formula for torque. If you remember, torque is equal to radius times force times sine theta. Well, if we have a perpendicular angle, then the sine just goes to 1, and it's just the radius, which is in this case the length of that half of the rod, the radius times the force produced. And they used that, Mr. Coulomb used that in order to figure out the charge between those two different pith balls. Now, what's really great about this is the wire and the torque on the wire is actually really, really, really sensitive. It doesn't take much force at all in order to make it turn. So you can have really small charges on those pith balls in order to measure how strong that force is. So you can see here's a nice photograph of an actual setup of a torsion balance. And again, a torsion balance is a very sensitive machine that is able to get really, really sensitive values of these forces. Here we just have another example of an illustration of a torsion balance. So you can see here that this ball on the left is charged positively, and then here we have a neutral charge on this ball. Now, because we need two separate charges in order to have an electric force, the charge on this ball is neutral, so it doesn't count towards our electric force. So because of that, we don't actually have a force that's being felt on this balance. So as you can see, there's no torque being generated. However, on this side, we have a positive charge here and a positive charge there. So they're going to want to repel each other. So as this one wants to push away, we end up with this torque that goes counterclockwise as they repel each other. So makes pretty clear sense, I think.